Supermassive black holes are beasts. They're difficult to observe and measure, yet their effects on their host galaxies are profound. Read up on the latest black hole discoveries. Despite their name, supermassive black holes are tiny relative to their galaxies. Still, they typically have masses of millions of billions times the mass of the Sun, guzzle any gas nearby, and pump out plasma, heat, and radiation at levels that affect the evolution of their hosts. We're still trying to understand how these black holes and their host galaxies evolve over cosmic time. Astronomers at the American Astronomical Society meeting in Washington, D.C., presented some recent findings that will change our understanding of how supermassive black holes affect the galaxies they live in. Weighing supermassive black holes. Measuring the mass of a supermassive black hole is harder than you would think. You can't exactly pop it on a scale. Astronomers can't observe them directly in telescopes either, at least, not yet. For relatively nearby galaxies hosting black holes in their cores, astronomers can measure the motion of central stars and gas to obtain a precise measure of the mass within them, but at greater distances even those central motions can't be resolved. So astronomers use a technique called reverberation mapping. Gas-guzzling black holes emit light at constantly changing levels, depending on how much gas the black hole is feeding on. This light strips electrons off gas in faraway clouds, which emit their own light at specific wavelengths. By observing how long it takes for a change nearer the black hole to travel out to the clouds, as well as measuring the motions of the clouds themselves, astronomers can precisely gauge the mass of the black hole that the clouds are orbiting. Artists' rendering of the inner regions of a supermassive black hole and the disk of hot gas that's falling in. The inset shows that when gas near the black hole gets more or less bright top panel, the gas in clouds far from the black hole reacts in the same way, but delayed by the time it takes light to travel to the distant cloud's bottom panel. The time span covered by these two light curves is about 6 months. NACS TREHN www.nacs.com and Catherine Greer, Penn State, and the SDSS collaboration. This spectroscopic technique has mostly been applied to relatively nearby black holes, in part because it takes a lot of observing time to obtain a single measurement. But now Catherine Greer, Penn State, and colleagues have used the Sloan Digital Sky Survey to measure black holes' masses in this way out to almost 8 billion light-years away, when the universe is about half its current age. The project, which began in 2014 and has collected 44 black hole masses so far, is still ongoing, with many more to come. A large sample of black holes near and far with accurate masses will help Greer and others understand how black holes evolved alongside their host galaxies. Revenge of the dwarf galaxies. Even dwarf galaxies can experience the wrathful feedback from supermassive black holes. Black holes with a mass of millions of billions of suns are known to emit winds, jets, and radiation that can quench star formation in their host galaxies. But dwarf galaxies have central black holes with smaller masses and less activity. Samantha Penny, University of Portsmouth, UK, and colleagues observed 69 dwarf galaxies that are no longer forming stars, using the Mapping Nearby Galaxies at Apache Point Observatory Manga survey. Most of these dead dwarfs live in crowded environments, where interactions with other galaxies have pulled away star-forming gas. However, 6 galaxies appear to have quenched star formation on their own thanks to the supermassive black holes that lurk in their cores. Manga spectra show the motions of stars and gas throughout revealing the signature of galactic scale heating driven by supermassive black holes. This is the first time feedback has been seen from such small black holes. While exact masses aren't known, they're probably less than 1 million solar masses each. This composite image shows one of the dwarf galaxies studied by the team next to a Milky Way-sized spiral for comparison. The dwarf contains about 3 billion stars, while the spiral contains about 300 billion. The inset top right shows a larger image of the dwarf overlain with some of the manga data for this, which revealed the winds from the supermassive black hole. Darker purple regions show gas heated by winds from these central black hole. These winds heat gas clouds that would otherwise form stars. Samantha Penny, University of Portsmouth, and the SDSS collaboration. Black hole feasts and burps. Twice astronomers have witnessed a black hole's eating habits using the Hubble Space Telescope and Chandra X-ray Observatory. Julie Comerford, University of Colorado, Boulder, and colleagues published the results in the Astrophysical Journal. The astronomers stumbled upon the nearby SDSS J13541327, discovering evidence for 2 black hole burps separated by roughly 100,000 years. Supermassive black holes feed in bursts, guzzling gas that unleashes radiation as it spirals inward. That radiation lights up the surroundings, stripping electrons off of neutral gas. In SDSS J1354, a cone of ionized gas extends 30,000 light-years south of these center, evidence of a feast roughly 100,000 years ago. A shockwave 3,000 light-years north of these center from the black hole suggests a more recent snack. The two meals were probably the result of interactions with a nearby companion. An image of the SDSS J13541327 taken with a Hubble Space Telescope and the Chandra X-ray Observatory. The top arrow points to a recent burp from the supermassive black hole, the bottom arrow points to an older burp. The two burps followed feasts on gas stolen from the larger companion above it.